Uh, Good morning, everybody. Let's start for our talk for today. This Saturday is my son is calling me. Let's start for our LAFMAT, our Latin American Network for Condensed Matter Physics. This seminar is occurs all Saturdays, and this network includes universities from several countries in Latin America, in, in Argentina, Bolívia, Brazil, Chile, Colômbia, Costa Rica, Equador, El Salvador, México, Peru, and Venezuela. There are 18 universities in these countries belonging to this network. For today, our speaker is Marco Schiavon. He's full professor of Federal University of São João del Rei. Please, Marco, if I speak something wrong about you, please correct me if I'm wrong. I did I made a search in your CV to make this introduce about you. And Marco Schiavon made the undergrad in chemistry at USP, and also the undergrad and master at USP in São Paulo. His PhD was at Unicamp, and then his postdoc, two postdocs, one at US in Arkansas University, and the second at Unicamp. His Mark also was a visiting researcher at several universities, including US and France. He's a very active uh, researcher with hundreds of articles, 160 articles, and much more. And he supervised several students, and today he will speak about carbon dots. Marco, thank you for accepting this invitation, and please, the floor is yours.
Okay, thank you so much, Mario, for the invitation to present part of my work and also for this network that I think is very interesting network. So today I'm going to talk about part of my work that is sustainable technology, how carbon dots are transforming material science. So as he said, I am from Federal University of São João del Rei at Minas Gerais State, and I'm a leader of a group, a research group that is called Grupo de Pesquisa em Química de Materiais. So I'm a chemist. Um, I'd like also to make a special thanks to LAFMAT because, as I told you, it's a very interesting network. And I take a look at a glance in the seminars, and I see that I'm going to present something a little bit different from the topics that physicists are habituated to discuss. So I hope to give you some new ideas and to be a pleasure talk. So in my research group, we have started to work with quantum dots. So I'm a chemist, and I work mainly with synthesis of quantum dots. I started to do this, but after that we have started to study also carbon dots, and after some perovskite nanocrystals. So these three kinds of nanoparticles has in common their optical properties that is very interesting from the point of view of technological applications. And then you have started to work with them initially by synthesize and study the synthesis and the characterization of these nanomaterials, and then you have started to make some application of this. This include, for example, use these nanoparticles as sensing. For example, here is a carbon dot working as a sensor. We have also used in biological applications as biological markers. and also in solar cells. So I'm going to give you, today I'm going to talk specifically about carbon dots, and I'm going to give you some examples of the utilization of carbon dots in energy conversion, for example, and also in new applications. And this is the why I have called the seminar How Carbon Dots Are Changing the Material Science. Okay? Um, so in all this, all my work, we have also three main ideas to improve life quality, to work with technology, and also environment. So I will be brief. So I hope not to take a long time. So when you think about nanotechnology and carbon dots, they are nanoparticles because they have nanometers and optical properties, as I said before, and they have a treatment like the other nanoparticles. So they are nanoparticles of carbon mainly, even if they have in their composition most oxygen than carbon. Um, they have also low cost and they are easy to synthesize. So this is very important for applications, for large scale applications. So we have a lot of methods of prepare them, and they are very simple. There is an infinity of precursors. They are water dispersible. They have chemical and photochemical stability because they are mainly constituted of carbon nanoparticles. There is an image of them. And the main idea today is to modulate their properties at electronic level. So make some substitution of carbon by other elements that we in literature is always called doping. And what is most interesting from this nanoparticle is their surface, because there is a lot of functional groups that has been explored a lot in literature to be used in this in different applications. So, by resuming carbon dots, they have simple composition, is mainly based on carbon, oxygen, and hydrogen, and also some adding elements. The most important is nitrogen. Also, um, elements with a low atomic number, for example, nitrogen, phosphor, sulfur, boron. So they have a simple composition. They are nanoparticles. They have sizes about 3 nanometers. They have been discovered accidentally in 2004 and synthesized for the first time in 2006. They are predominantly non-crystalline nanoparticles. There is assumed in literature that they have a core with mostly sp2 carbon and a surface with sp3 carbon. So they are very successful used in passivation and with doping with these elements I have said before. And it can be have their properties modulated mainly by the electronic levels by using these elements that change some of their properties. And they have all the applications is based on the optical properties they have. So most carbon dots have a blue luminescence. They are considered new carbon materials. So their optical properties, as I said before, it's very important. They have most of them. They have blue photoluminescence. That it's a limitation, and most of research today is based on change this luminescence for other parts of the UV visible spectrum. They have generally spherical morphology, and as I told, functional groups that it's the very important part of them. So, properties of carbon dots. They have chemical stability, solubility, they have low toxicity, they are biocompatible, and easy of preparation and low cost. So these are features that make them very interesting candidates for large scale applications. So about the applications of them, we have, as I told before, as a biological markers, as sensors, in photocatalysis, there's lots of studies, and also in LEDs, they have been used, and in solar cells. And the new, the most important, I would say, the most impressive application and commercial in Brazil is the use in growing of plants. So I'm going to give you example of applications of carbon dot in solar cells. That was my initial interest in this material, and in growing improvement of the growing of plants. So our interest in carbon dots, so we have written a review in Portuguese about carbon dots, and this is the interest in carbon dot in literature is very impressive, because for you can see from 2008 to 2022 or 21, that is our last revision about the literature numbers. There is more in 2021, more than 14,000 papers about carbon dots. You have used, for example, for the research, the words carbon dots, carbon nanodots, carbon quantum dots, and graphene quantum dots, that are names generally used for this kind of materials. So then we have a dispersity of names in literature, and the classification of carbon dots. When you say carbon dots, it's a general name for different kinds of nanoparticles. Sorry, it's in Portuguese, but you have graphene quantum dots, quantum dots of carbon, that is mostly based on graphene too, nanoparticles of carbon, and polymer dots that are novel of quantum dots. So generally use the name of carbon dots. In the beginning of the about 2012, for example, some people say that they have a quantic effect, but it was not proved this. So even in literature, most people say quantum dots, carbon quantum dots, the great majority of articles published are not quantical effects. So they are not like quantum dots of semiconductors, for example. But there is this name is very common, and I think if some people would like to use this to improve the kind of nanomaterial or something like that. But they don't have, most of them, I say, they don't have quantic effect in this kind of nanomaterials. I'm going to discuss this about later. So, about the preparation methods, you have two typical methods, that it means top down and bottom up. You have different kind methods of synthesis. When you say when you start from small molecules, small precursors that are organic molecules, of course, to generate carbon dots, and you have some greater structures of carbon, for example, carbon nanotubes, or biomass. That is the most common, for example, today, to use biomass to prepare and by top-down method carbon dots. And we have an infinity of precursors. Even if we are talking about organic molecules and about biomass. So when you work with small molecules, organic, the studies intends to study the functional groups that we can control, because till now we don't have a control of these nanoparticles when we start from a precursor to understand how to modulate the final nanoparticles. But to use small molecules, organic molecules, is the aim to try to understand how we can control the surface, for example, of the nanoparticles. And there is for the bigger materials, for example, the biomass, today is the most studied because of the possibility of application in large scale, as I'm going to give you an example. So, and about the optical properties of carbon dots. So, carbon dots are mostly, they have mostly a blue luminescence, and they, as a material constituted by just carbon, oxygen, hydrogen, and some other elements of low atomic number, even they are nanoparticles, we use the organic orbitals to explain their photoluminescence, their excitation. And here we have some samples of different carbon dots with different luminescence. So we have used the orbitals and not say, is not used HOMO LUMO, for example, or the valence valence band and conduction band. Okay, so most in the literature you have two kinds of luminescence of carbon dots, and you have say that for some kind we don't have a, a maximum a maximum emission when you vary the number, the excitation wavelength. So, and for other kind, you have different maximum emission for different excitation of wavelength. So this case was the one that makes some people believe in 2012, 2010, for example, that this should be a quantum confinement effect, but it was not. So uh, these two main behavior of luminescence is believed that we have homogeneity of surface groups in the nanoparticles. When you have homogeneous groups and homogeneous surface, you have independence of the emission by the excitation wavelength. Otherwise, when you have non-homogeneity of surface groups, we have this dependence of the emission properties uh, that depends so on the wave excitation wavelength, and this is assigned to different levels, sub-levels that are created between the HOMO and LUMO. Even I told you that we not use we use HOMO LUMO as a kind of a molecule, né? It has been treated as a kind of molecule. So this is the most accepted explanation in literature to explain the photoluminescence effects of carbon dots. So Today, it's also possible to prepare multicolor carbon dots using the solvent engineering, using the solvatochromism of these molecules because there is different surface groups, and then you can these groups can interact with solvents in different ways and give it colors of luminescence by the solvatochromism. And there is, for example, in our last research about the number of publications, 2023, for example, it's about 400 articles using this strategy to prepare colored carbon dots because they have some applications. For example, for solar cells, it should be interesting to have um, carbon dots absorbing, for example, in the not in the blue, né? Not in the blue region. So this is the why they are studied. So I'm going to give you now an example of carbon dot in energy conversion. The first article, it was a cover of the journal Material Chemistry in 2012. That is, carbon dot was used in the dye-sensitized solar cells as a green nanoparticles, and they proved that there is an effect of energy conversion in solar cells, in dye-sensitized solar cells, where the dye was the carbon dots. The conversion of light was very low, much lower than 0.1% of conversion, but it demonstrates that it's possible to use these nanoparticles in energy conversion. So you have then studied some carbon dots via pyrolysis using some precursors. Then you have performed a pyrolysis in an oven, make some extraction of the nanoparticles because generally they are immersed in a in bigger in bigger particles. That is not a interesting properties. And then we have tried and have made some dispersion of the carbon dots and have seen the luminescence in blue. So one of the strategies of our preparation was to use carbon dots, for example, from these different kind of precursors. The idea, for example, is to use a carbon dots from citric acid because they just have carbon, oxygen, and oxygen. This molecule, for example, there is a lot of nitrogen groups that has been proved to be a group that changes the electronic levels and increases the photoluminescence of the nanomaterials. This another one. This is another molecule that have considerable number of nitrogen in his structure. And this is mercaptopropionic acid. Then we have a carbon and also a sulfur atom. So we have prepared different compositions of these nanomaterials to try to understand how these groups could influence the energy conversion, for example, in a solar cell experiment. So we have this five compositions of nanomaterials. Then you have characterized them by their quantum yield, photoluminescence quantum yield. That you can see there's not too much high for some of them, and the excitation, the lifetime excitation. So you can see that there is no high values of excitation, and their photoluminescence is typical of carbon dots that they all of them most of them presented the effect of inhomogeneity in their surface, changing the excitation, the emission maximum with different excitation wavelengths. So They are typical carbon dots, and they have also characterized them by UVVs spectroscopy. And you see that for the most important sample is the APC. I'm going to show you. And we got this spectrum that we have a P star, a sign of this band that was the most important, most well formed in this nanomaterial. So the IV profiles in DSC, where you use um, was for the this red one, that is for the this carbon dot that is an APC. The APC, just to remember you, is the one from citric acid and this molecule that has a lot of nitrogen atoms. So this nanomaterial gave you a conversion of energy of 1.3. This is a high value in literature for up to now for the a carbon dot in a solar cell. So you prepare solar cells in our lab in a artisanal way. So they are now it's not clipped anymore, but they are sometimes you clip them to make the device. So and we got this that is a high. So we try to understand why this carbon dot, this composition was the best one, and you have performed some XPS analysis of these carbon dots to understand their surface, because we know that today that the surface of carbon dots is very important for their properties. And this carbon dot was the only one that presented the amide uh, bonds. So the other one have hydroxyl, carbonyl, carboxylate, but this carbon dot was the only one that presented this amide bond. So we are studying the use of precursors that to confirm this, to precursors that can um be able to produce amide bonds. But I have also seen in other works that you need to have carboxyl groups, because when you use carboxyl groups, the nanoparticles can be attached to the semiconductor titanium dioxide. So if you don't have carboxyl groups, we don't have the attachment of carbon dots, and the solar cells doesn't work. So, but we are particularly interested to have so the carboxylate group to attach the nanoparticles, and also to have this group to confirm that this group has a special contribution for the energy conversion in solar cells. So such kind of work is much more basic. So we use these controlled precursors to get these results. But I have also used some abundant precursors in solar cells. You have used in another work, for example, wasted coffee powder to prepare carbon dots, and also gelatin to prepare carbon dots. So we got different results, and we get here a higher conversion for the wasted coffee powder precursors of carbon dot that and you have characterized then also, and have seen that you have some amide groups also in these nanomaterials, and it was not found in the gelatin uh, carbon dots prepared by using gelatin. So we have got a 0.53 energy conversion for the coffee, wasted coffee powder precursors, and 0.2% of conversion for the gelatin. And so it's another evidence of this group. So you have also performed some stability studies of these uh, solar cells using these carbon dots, and you have seen that they lost easily. So that is another problem to be solved to prepare solar cells using these organic nanoparticles. So then we have seen that there is a lot of work in literature about applications, and we decided to study also the biological and ecotoxicological study of carbon dots derived from wasted coffee grounds. So going to the line that to use biomass products because of the possibility of application, as I'm going to give you an example of a commercial product in Brazil. So we have used wasted coffee grounds, and you have prepared carbon dots by using a pyrolysis method. Also, here there is an image of under excitation of the carbon dots prepared, and we have studied the behavior of this in biological systems in vivo and all in vitro, and also make some ecotoxicological tests using zebrafish as a standard. So, this is, as I told you, we studied this because carbon dots derived from wasted coffee grounds. Brazil, for example, is a great producer of coffee. There is a production in millions of sacas of 60 kilos. That means, for example, in 2003, 2004, 10.5 million of tons of coffee. There is a composition of the main components of the coffee, and we have wasted coffee grounds about 1.1 million tons by year. So this is very important to have an application for this, and maybe why not to prepare carbon dots for application. But you are different from most application in literature. You were worried about the biological and the impact of these nanoparticles in biological systems. So these carbon dots have a very typical emission that is the most important feature of them that explain the use a lot. So they have a large emission, and here are two samples that you have prepared for this one, and you have used just this one for the tests you have performed. So, um, so we have started with in vivo toxicity tests. It was um, very difficult to work to for us to understand. For example, we have to a committee of ethics in the university to approve to use mouses from 6 weeks of life. They have to have a special cares with feed, cleaning of the place they are, the weight of them, and the evaluation of the straw cycle. We use the females to perform this study because they are more sensible to for such kind of study. So after the 8 week, we have started the administration of the nanomaterials. You have used different doses for them. The first, after the application of a dose of carbon dots, for example, you have to observe them for the next 4 hours. Then you have, if you don't observe any problem with the mouse, we made another dose. And after the 14th day, we have then they were died and they have the blood collected, and also some organs, for example, heart, lung, liver, kidney, to be studied. So here are some results of this. Um, you have seen they when you compare with the control, they do not have a high toxicity, so that's very good. And they have just some concentrations in liver. And this is the date, the hemogram, and the weight for this for a dose of 2,000 milligrams by kilo of the animal. So it's a very high dose. So when you compare in this article here, we have used the same study, but you have studied the quantum dots of carbon it's a semiconductor ternary quantum dot that's made by with copper, indium, and sulfide. That's the most studied carbon quantum dot for green applications. And for this for this quantum dot, this dose of 2,000 milligrams by kilo was lethal for all the animals. So for carbon dots prepared from coffee waste was not lethal. So that's a good result, saying that they have a low toxicity. Then we have performed ecotoxicity tests, also using the ethical permission of the ethical committee of the university. And we have used the zebrafish, the embryos of zebrafish, because the embryos can be they developed themselves from 0 hours to 96 hours. So in 4 or 5 days, you have a complete cycle of experiment. So we collect the embryos, and you have used 20 embryos for each concentration of the carbon dots. So and then we analyze the the behavior of these carbon dots in these embryos. So we have seen, for example, when you have a control and compare with different concentrations of carbon dots, 150 micrograms, 200 micrograms, 250 micrograms, and 500 micrograms. And we have seen that for 500 micrograms, you have a mortality of the embryos about 50%. So uh, this is according to Fish and the Wildlife Service. Uh, we understand that up to the concentration of 50 milligrams per liter, it can be considered practically non-toxic. So we have seen they have of course they have a toxicity, but it is it is not so high. So for 1,500 micrograms of concentration by liter of the solution, you have seen cardiac edemas and also the death of the embryos. So as you can see here in this control. So even with these results, they can be considered practically non-toxic. So for for a green quantum dot for a copper indiosulfide, for example, as I told you before, the all of the embryos were died. So indeed, carbon dots are much less toxic. So then we continues in this line of using now pyrolytic lignin as precursors of carbon dot. We have a collaboration with another group from another university in Brazil, and this is a very pyrolytic lignin is a extract from the bio oil from the wood, and there is a large production in Brazil also. And then we have used hydrothermal carbonization and have prepared some nanoparticles. And then you have studied the photoluminescence and tunable optical properties, trying to characterize, to obtain carbon dots, suitable carbon dots for applications using this biomass. So you have also used the lignina craft as precursors of the carbon dots, and you have performed a technical economic analysis and optimization using, for example, ethylene diamine doped carbon dots. So you have introduced the nitrogen in this nanomaterial, in these carbon dots, to improve their optical properties, uh, starting from this product of the industry of wood, that is the craft lignin. And you have also here used the hydrothermal process, that is a very common method of preparation of carbon dots in literature. So we have characterized them by several techniques, and we have seen that all these nanomaterials has the similar behavior, optical behavior, as others in literature, including the commercial one that I'm going to show you later. So they are suitable for application in large scale. Um, And then there is a concept in literature that they called closed loop. That means photobiosynthesis improvement by means of carbon dot derived from biomass. So you can use biomass to prepare carbon dots, use them in a plant to improve their photosynthesis. That means you can produce more with this plant, and then reuse it in a production of another carbon dot. So this is an article that has been published last year by a Chinese group that they called closed loop enhancement of plant photosynthesis via biomass derived carbon dots in biohybrids. So uh, this idea actually is not so new because they have been used. But the idea of the article is to use different parts of the, the, the plants for leaves, weeds, straw to prepare carbon dots that can be used to to be manufactured, to be used in plants, and this would promote the improvement growth of the plants, increasing productivity of different kind of materials of interest in agriculture. So and they claimed that the nanoparticles, the carbon nanoparticles, the carbon dots, uh, can be accumulated in the membranes and also promoted by emitting when they have the sunlight, and by emitting blue color, they can improve the photosynthesis intra-plant. So here there are some images of different carbon dots produced from different parts of these plants. For example, from straw, you can see here we have a cyano carbon dot. From leaves, for example, we have a green carbon dot, and so on. So this is very interesting from the point of view of the production in agriculture, but there is no knowledge, there is no results, there is no studies to prove, to demonstrate how carbon dot can be accumulated and how can be consumed in the by the plants and so on. So here there is some studies they have used this paper I'm talking about. Sorry, they have used these plants, que é Arabidopsis thaliana, and they proved that they by administration of some concentration of this nanoparticle they can improve the fresh weight, for example, of the plant, and the area of the leaf can also be improved by this. That means you have a higher productivity when you use this in agricultural plants. So this is very interesting, but there is no studies about the physiological point of view to demonstrate how these carbon dots can be consumed, for example, in the plant in the future. Or if you, for example, if you were in a production of lettuce, if you can eat this a carbon dot with a lettuce with carbon dot, what is the result? What's the impact of our life? So this is the point. So even if you have a closed loop, there is some points that we need to improve about this. So, and in Brazil, we have a commercial carbon dot uh, dispersion it's produced by a Cryotech and it calls Arbolina. So this Arbolina is a Brazilian foliar biostimulant that is applied by aspersion of the leaves based on carbon nanoparticles. Is a carbon dot, and it has been developed by researchers from University of Brasilia and Embrapa, that is agricultural company in Brazil. And they claim that this technology increases photosynthesis by up to 50% in the plants, improves nutrient uptake, enhances plant resistance to drought. So this is very important from the point of view of increase of production, because this condition increase resistance, enhance plant resistance to drought is very important for large agricultural fields, and boosts productivity up to 40% across various crops. So this is a startup. It starts as a startup in the University of Brasilia, and there is this commercial product. And when you compare the optical properties of these materials, of this commercial one, is similar, very similar to the one we have already studied. We have a lot of examples in literature for different biomass. So when you analyze the instruction of use of Arbolin biogenesis, that's the name, technical name of the product, there is in Portuguese, and I put it here in Portuguese to see. to show you that this is the reality. So all the information about, for example, mutagenicity in germinative cells, carcinogenicity, toxicity to reproduction, toxicity for uh, parts of the human, toxicity for non-specific organs, ecotoxicity. In all of them, it is not expected. It is not expected that the product presents some of these properties, some of these characteristics. So ecotoxicity is not expected. So persistence and degradability, it's expected a quick degradation and low persistence. So um, in all the capitalism system, né? So there is commercialization, but there is no studies that can support the use of this for large use. And we have seen, for example, that carbon dots from a wasted uh, coffee grounds presented some toxicity, ecotoxicity, and also some toxicity in vivo and in vitro. So uh, it's uh, it's another way to think, but that means that even we have a commercial product, we still need to uh, keep studying this kind of materials. So for you have an idea, the 1 liter, there is 500 grams by liter, so it's very concentrated carbon dot dispersion, and you can find it in Mercado Livre, for example, by the price of about 200 USA dollar. So, and it has been commercialized largely in Brazil now for most product. So, the future of carbon dots. So they have a cost about 6 USA dollar by gram, about, né? Or depends of the concentration. So it's an interdisciplinary area that is growing the development because the main interests may be large scale production, as we have examples of this. The biomass use that we solved a problem, and it also has the idea of to have a closed loop of photosynthesis. Uh, but studies of structural modifications is also important to improve the quality and the properties for other applications, for example, the nanoparticles. So property improvements, it's very important at this time, and also fundamental studies to give us more support. I would say or highlight that toxicity is very important in studies, and for us, it's an interdisciplinary area. Ecotoxicity and secondary effects on biosphere. So such kind of studies is very important. So I have associate now with groups from biologists to start to study this, to make some changes in the carbon dots, comparing with this commercial one, for example, and to study the toxicity, ecotoxicity, and secondary effects on biosphere, because I think this is very important to have upgrow a really development of new products from nanoparticles in nowadays. So this is our research group. We have a page. You can check out other works that we do that. So this is an image of the group from the last one. So we are at São João del Rei, Minas Gerais state. That is a historical city in Brazil. Historical, I means 330 years. So, but it's a historic one from with a strong influence from the Portuguese colonization. The university at São João del Rei, you have three campi, and in our campus we have 16 undergraduate courses, 9 graduated programs in the areas of social science, medicine, and natural science. That is our uh, program. So in our department, the department is natural science. We have physics, chemistry, and biological courses, undergraduate courses. We have also 4 master programs and 2 master programs. So I'm part of the program of materials that calls FK, FK Mat, that is Physics and Chemistry of Materials. And we have a good a structure in our lab. And I would like to thank the agents, Brazilian agents, that help us to develop the studies of in our group. And would like to thank you for the attention and to listen to me. So I'm open for questions and comments.
Marco, thank you for your nice presentation. I will open the section of questions following here the order that people are appearing to me. Vivian Gonzalez, do you have any question? You said here in the chat that the talk was interesting, but do you have any questions to address?
Just a little question. Thank you so much for your talk. It was very interesting. But I would like to know if there is a specific synthesis method that is with higher yield in quantum dots, for example, which is the best in that case, I mean.
Yeah, the most studied method of synthesis is hydrothermal.
Yeah,
But the problem of the hydrothermal method, for example, it takes some hours. So
yeah,
sometimes you have 6, 8, 10 hours to get the product. So, but they give the highest quantum yield, photoluminescence quantum
yeah.
yield.
And you know,
We are testing the microwave now, and
okay,
we are going to compare the photoluminescence quantum yield of them. Because in
okay,
the microwave you have a 30 minutes, so it's very easy.
okay.
Yeah, it's
Very
very rapid to prepare.
because well I try as you mentioned in the before, I try to make some quantum dots but are related with other nanomaterials, and it was synthesized by ball milling, and I want to know if it's possible. Maybe you are you know something related with ball milling or not about carbon dots.
Oh, I've never seen this using this
Okay,
method. Okay, I've never seen because maybe, but I don't know. I really don't know,
okay,
and I never seen in literature such kind of method for
or well,
synthesize
yeah,
carbon dots.
okay, thank you so much, it's all, thank
Okay.
you.
Your microphone is closed.
Sorry. Sorry. Yeah. Yeah. Stuart Holmes, do you have any questions? Stuart Holmes from UK. do you have any questions to address to Marco? Sorry, I called you before, but my micro was turned off.
Thank you, Marco, for your excellent presentation. Thank you. I have some technical questions. You mentioned the APC solar cell, which had an quantum efficiency, power conversion efficiency of about 1%. So, do you know what the internal efficiency is? Presumably, that's the external. Is there an internal efficiency which might be a lot higher?
Yeah, we don't have measured for this kind, so sorry.
Yes.
It's very hard to get some kind of measurement here in Brazil. It's not common. So we are just asked to buy equipment to measure internal quantum
No,
efficiency.
I understand. Thank you. Thank you.
Yeah, I'm
I have another.
sorry.
That's okay. That's okay.
When you get some results from collaboration with other universities, so it's not easy.
Yes,
I'm
absolutely,
sorry.
absolutely.
For that, we don't have.
Could I check the construction? You use titanium oxide as a metal. Is it a metal? Is that a metal contact to make your external circuit?
Yes, we have used so we have a FTO, and then you have a blocking layer of titanium dioxide that's made by deposition.
Yeah.
It's a thin layer, and then you have the titanium dioxide nanoparticles that has been deposited. And then we have made the sensibilization of the titanium dioxide active layer by immersing them in a dispersion of carbon dots for 24 hours. And then you have the titanium dioxide sensibilized by the nanoparticles. We wash, dry them, and then we prepare the counter electrode that can be a copper sulfide layer. And then we make a channel to put the electrolyte, the liquid electrolyte, that's iodine, and closed the device.
Thank you. That sounds interesting. I have one final comment, and in the synthesis of your carbon dots, you didn't mention the word fullerene. Do you ever get an appearance of some, the carbon-60 structure when you're making carbon dots, or is that, which are known to be stable? Is that just never appears, the carbon-60?
I'm sorry, I didn't understand. What do you?
There's the fullerene, so-called fullerene structure is a carbon dot, carbon-60. Does that ever appear when you try to fabricate carbon dots, or is it just it never happens?
No, I don't think
it
so.
Doesn't. It just never appears.
No.
The so-called buckyballs, right?
Okay. Yeah.
It never appears. It must be that they are grown under different conditions.
Okay.
So you're lucky they don't appear.
Okay.
Okay. Thank you, Marco. Thank you for answering my questions. Very interesting material. Thank you.
Thank you.
Thank you, Mario.
My micro is turned off again. Thank you, Stuart. Let's move for Carlos Rudamas from El Salvador. Do you have any question?
Hello, can you hear me?
Yes.
Thank you very much, Professor Marco, for the very, very interesting talk. I have two questions, but probably more. But the first one is, what do you think, why people are not able to see the quantum confinement effect in carbon dots, considering that we could have a exciton Bohr radius very high? This is the first one. That is a very fundamental question. And the second one is, if you have explored the use of carbon quantum dots in nanofertilizing. Okay, this the first two questions. Yeah, thank you.
Okay, so concerning the first question that you have about you asked about the relation of the carbon quantum dots and the carbon dots, and why it was believed that it was a carbon quantum dots.
Yeah, but why
Yeah,
we are not able?
yeah.
Why we are not able to?
Actually, when people started to study carbon dots in literature, they observed this change of a maximum of luminescence using different wavelengths of excitation. So they said that, oh, it was a quantum confinement. But there is not. There is a paper also that demystified this problem by explaining that some people generally use the FINDA. It's the equipment of a spectrometer of photoluminescence. There is some FINDs that's openings, and they when you are in the excitation in higher wavelength, sometimes you can see the second harmony of the nanopart of the emission. So it's not the confinement. So it's just an effect of the surface of the nanoparticles and not the quantum confinement. So because the quantum dots is quantum confinement is very common in literature for binary nanoparticles, I think that this is the reason to believe this. And we have the same problem, for example, when you study, Professor, ternary quantum dots, because they are semiconductor quantum dots, but as they are ternary and they have possibility of change the oxidation number, they some people are not sure because they have there is not a relation with size directly with size. There is no direct relationship with size. That's the problem, and people start to believe that the quantum confinement. But after that, you have seen that all the nanoparticles has the same size, for example, and they have that change of emission peak. So. I think this is because of a fixed idea of secondary binary semiconductor quantum dots. That's very clear, this effect of quantum confinement. But as for ternary, quaternary quantum dots, we can have composition effects and not a size effect in quantum confinement. So this is
Exactly. Probably the most important thing is interpretation of the transition bands, what they are observing.
yeah.
Exactly, because we don't expect this quantum confining effect when
Yeah.
we are looking surface states, for
Yes.
instance, but only when we, for instance, observe, let's say, a free exciton transition or something like that. No?
And your second question was? I don't
The
remember.
second one, if you have explored the use of quantum dots as nanofertilizer.
So no, we are going to start to do that. We have just started with a PhD student to prepare some carbon dots with different structure, not different composition. We are going to use the phosphorus as a doping element, because this has also important role in the photosynthesis in the plant development. And then we are going to prepare and to try to study this and compare with the commercial one, for example. This is a collaboration with some physiologists of plants from my university, for example. And this is the idea, to prepare different carbon dots now and to apply them. But we have some ideas of modification by introducing some elements, because the commercial one, I didn't say, but it's always carbon and nitrogen in
Okay.
their composition, as said by the producers. And
Okay.
then we have seen that there is other elements, and we have also, Professor. For me, I think it is the most important is to study, try to follow the nanoparticles uh, during the development of the plant, because we don't know. It's believed, it's expected that the nanoparticles will be consumed by the plant, but there is no studies. And then we have now um, equipment that is that we can obtain the images of the plant. I forget the name of the equipment that we can follow in the plant, or we can put the mouse there and make the measurements.
Okay. Oh, interesting. Thank you. Thank you very much. I'm very interested
Okay.
because I have a couple of students working with quantum dots and carbon quantum dots, and we will be in touch. I will send you an email in order to
Okay.
see for possibilities of interchange or collaboration or something like that. Thank you very
Great.
much for the very nice presentation, and congratulations for the nice job you are
Okay.
doing
Thank
there.
you. Thank you.
Thank you.
Thank you, Carlos. Let's move on. Henry Mondaca, do you have any questions? I'm really sorry, but I don't know what's your university and country.
Oh, okay. I'm Peru, San Marcos.
Okay, great.
Nice presentation, Professor Marco. Well, this
Your
is not my
camera,
field of
please,
research.
Henry. Your
Oh,
camera.
my camera. Okay, sorry. Okay. Well, as I say, nice presentation, Professor Marco. My question, well, this is not my field of research, so my question is more like interesting about what the possibilities are in this area. So, one of the properties that you mentioned about these carbon dots is the luminescence, the photoluminescence of these elements of structures. So there are also uses in tracking cancer cells, because what I reading about is like they used to deliver it some treatment for cancer, but I don't know if they use it also for tracking cancer cells.
So, yeah, there is a lot of applications because of the surface groups of the carbon dots allow this possibility of making we have used in the past for to prepare sensors, for example, for metal analysis, and also a metal analysis of plants. So depends of the surface group you have. So this is a fundamental study to use to prepare carbon dots if fundamental groups that you can uh, boost, can help your the application you want to. I would like, for example, to make some conjugation of carbon dots with another nanoparticles, for example, to get like a nanomolecule, for example. But I don't have at this moment students to do this, so Sometimes it's not easy to develop, to put in practice everything you want. So, but I think there is an infinity of possibilities when you have a functional group on surface, because you can also make a reaction, very simple reaction, to attach other groups and change the properties. For example, some people use polymer to make a involucre of the nanoparticles to get another properties, for example, for drug delivery, such kind of this. But I think it's very important to know the functional groups you have. So for this, you have to make a characterization of XPS, for example, and infrared, for example, to know about the functional groups you have there. Otherwise, it will be difficult. I think it was this. I
Yeah,
answered your question.
yeah. Other curiosity. What are the computational developments in modeling these nanodots?
And modeling.
Yeah, modeling, mathematical modeling, computational modeling. All this.
Yeah. You have tried to do this with some researches of theoretical chemistry, for example, but you didn't get any results, because I think there is a complexity of these nanoparticles, because even it was believed that the core is mainly by sp2 carbons, you have some sp3 there. And I think this is not easy for theoretical studies too, because I think by what they have, some researchers that I have contact said, oh, you need a very powerful machine to make this calculation with a lot of atoms, with a lot of if a core, a considerable core. So I don't know.
Yeah, I guess they use supercomputers to model these type of
But there are
structures.
some studies that have seen that when you put nitrogen in the structure or other elements, you have sublevels created that, with different energy levels that make changes in the photoluminescence, for example. There is some theoretical studies of simulation using this kind of doping.
Okay.
Okay.
Okay. Thank you for the answers. I appreciate a nice presentation. I really learned something new here today. Thank you.
Okay.
Okay, thank you. The next one, Sergio Paniagua. I'm sorry, I don't know your university and country. Do you have any questions?
Yes, thank you, Professor Marco. Yes, I'm from Costa Rica, from the
Great.
National Nanotechnology Laboratory. So we actually have some experience with carbon quantum dots as well. And the system that we focused on was the citric acid reaction with urea. And we tried both microwave synthesis and also just batch reactor hydrothermal synthesis. And in both cases, we noticed there was a lot of byproducts, like small molecule fluorophores that we needed to purify. And first we tried simple things like ultracentrifugation and dialysis, but that didn't really work for us. We ended up having to do column chromatography to purify the carbon quantum dots. So I'm curious what your experience with purification has been with your precursors and your way of doing the carbon quantum dots.
Okay. So you said you have used carbon, carbon nitrogen
Yes, citric acid
nanomaterial.
and urea, so it's nitrogen doped carbon
Okay,
dioxide.
yeah.
Yeah.
So in the beginning of our studies, we just make some filtration of the materials. We saw that there is some it was not pure, but now we have used dialysis. Or you have a membrane, and then we put the solution, and we have a cut edge of 1 kilodalton,
Mhm.
and then you have the carbon dots inside and something that is not the carbon dots outside of dialysis after 24 hours. So this is a very common method for purification nowadays of carbon dots. So you have using this membrane for dialysis to purify them.
Okay. All right. Thank you.
Thank you, Sergio. Moving on, Thomas Rojas, also from Costa Rica. Questions?
Hi, good morning. Actually, I just had a question, but it was aimed at whether or not they had done theoretical calculations, which you already answered during Henry's question.
Mhm.
So no, just to say thank you for the very good talk, and it is indeed a very interesting topic.
Okay, thank you, Thomas.
Thank you, Thomas. And to conclude here, the panelists, Ximena from Colombia, you and the students, do you have questions, the students?
Good morning, Professor Mario Reyes. No, in this moment, we don't have any questions about our social networks. And for me, I don't have any questions. Thank you, Professor, for your incredible talk. That's it. Thank you.
Thank you.
Thank you, Ximena. And to conclude, Marco, I will have some comments in the chat. Sergio Conejeiros from Chile, and Arturo and Alfredo from Mexico, and said the talk was very nice. And also Luis from Peru said that the talk was very nice, and congratulations for the talk.
Oh, thank you.
And to conclude, Marco, do you have any final words to conclude the talk for today?
Yeah, I just would like to thank you for invite me and to permit to make this presentation. And when you come to Minas Gerais, São João del Rei in Brazil,
Sure.
please come to visit our lab, and we are all open for collaboration because unfortunately till now I don't have any collaboration if America, Latin America. So it should be very interesting, exciting for me to have this possibility. So
Okay,
thank you.
thank you, Marco. And to conclude, people, let's open the camera to say goodbye, and I wish a very good weekend to everybody.
So thank you
Bye-bye.
so much. Bye bye.
Okay,
Thank you.
bye-bye.
Bye-bye.
Goodbye.
Bye, everyone.
Thank you very much.
Thank you.